Okay, and we're recording, right? So last time we were talking about, we were working our way up to defining a new kind of integral. We didn't really say so at the time. We started off just looking at parameterizations and thinking about what happens when you hold one of the variables constant and you get these coordinate curve things, blah, blah, blah. What we did end up with, though, and this is where we had to leave it, was that when you have a parameterization of a surface, you can basically look at a piece of area over here in the parameter space, and you can see how big its image is by looking at the corresponding vectors, how big its image is over here in the surface space itself. Right? So specifically, here was the calculation we ended up with. The surface area is, it's a certain factor times this original input area. Or you might say this differently as the area increases by a factor. And as usual, I'm going to call this a stretching factor. So output area bigger than input area by way of multiplying by this factor. Okay. All right. We also talked about how that factor is the magnitude of a certain vector that we're going to call capital N. This vector is more interesting than just by virtue of its magnitude being the stretching factor. There's other useful things about it. In particular, for example, notice that vector always perpendicular to the surface, right? Because it's a cross product of two vectors that are parallel to the surface. Okay, but we'll get to why we care about that a little bit later today. Okay, so this is where we ended it last time. So the thing is, with this setup as it is, we're actually prepared now to compute, for example, the total area of this sphere. Because the total area is the sum of a bunch of little pieces of area like this, and those little pieces of area can be written in terms of this little piece of area over here, and adding up little pieces of area in two dimensions is something we already know how to do. That's just a plain old double integral. So here's how that calculation goes then. Here it is. So computing the total area of the unit sphere. Well, we know that we're going to need this n vector. More to the point, we're going to need to know the magnitude of n. So I'm going to compute that first. And before we get into that algebra, let me point out it's a multi-step process. So first thing I have to do is have a parameterization. Then I've got to compute its partials with respect to the parameters. Then I've got to take the cross product of those partials, and then I've got to take the magnitude of that cross product of those partials of the parameterization, right? So there's several little steps that have to get done, and it's a little tedious, and I apologize. It's nature of the beast. So here we go. The unit sphere. I parameterize like this. And this is not, of course, the only way to parameterize the unit sphere, but y'all may recognize this one, right? This is the spherical graph parameterization of rho equals 1. You just plug in rho equals 1 into the coordinate conversion formulas, spherical coordinate conversion formulas. So spherical graph parameterization, neat trick. And then, as we just noted, partials, and then cross product, which is some algebra to be done. You end up with this. I'm glossing over, you'll notice, the tedium of this. I think it'd be a healthy exercise for y'all to fill in those blanks. Make sure that you can compute those partials and get the right answers. Make sure you can take this cross product and get the right answer. Real quick, I will point out that in order to get this third coordinate correct in that cross product, you are going to have to invoke the Pythagorean trig identity to get that to simplify right. So heads up on that. Anyway, make sure you can go through all that and do that. And then, with the capital N vector, you still have to take the magnitude, right? And that is a pretty non-trivial amount of algebra as well, making several uses of the Pythagorean identity. So there's a lot of algebra that I swept under the rug in this calculation. And again, make sure that you can do that. It's like I said, good healthy exercise. Okay. All right. So that said, though, here's the final conclusion, and that is that our stretching factor, very nicely, it's just sine phi. It's fantastic. It's that simple. That sine phi is our stretching factor. So if you're looking to take the total area and write that as the sum of a bunch of little pieces of area by slicing up the sphere, each little piece of area is a multiple of d phi d theta, and here's our multiple. Our multiple is sine phi. Everybody see what I did there? Okay. All right. And then these values of phi and theta run you over the entire sphere. Let's think that through just for a quick minute. Theta 0 to 2 pi just means you go all the way around, which you might call longitudinally, right? And then phi goes from 0 to pi, 0 being straight up, and then as phi increases, you kind of go down a meridian and gets to pi when you're going straight down. So these values just trace you over the entire sphere. And then it's just an integral to be computed. It's not even a hard integral. That's an easy evaluation. Again, make sure you can do that. And 4 pi, our familiar answer. Okay. What do you think? Questions? Everybody's good with that? All right. Okay. So here's a kind of a summary and then a slight supplement. We talked about, most of what we developed here, I mostly did in the context of spheres. But this is kind of the general form of it. If you have a parameterization, then the partials give you velocity vectors. And those velocity vectors are what you cross to get the normal vector, capital N, whose magnitude is the stretching factor. And you can think of that capital N as being a product. There's two interesting things about this product. One is, again, the magnitude here is our stretching factor. And you can see it right there, playing its role as the stretching factor. It's what you multiply by parameter space area to get surface area. But you can also see in here, breaking up this capital N into a magnitude and a direction. The little n is the unit vector pointing in the direction of capital N. It's the unit vector pointing perpendicular to the surface. Right? Again, because it's perpendicular to two tangent vectors. Okay. All right. So now just to supplement a little bit, the next little bit that I have on here is really a fairly innocent observation, but I'm just pointing out that if you were to take the S partial of a vector valued parameterization, well, partial derivatives, you just do one component at a time, so that's all that is. And then likewise here, the T partial, well, just one coordinate at a time. And once you have that written down, then you can say, well, I can actually crank out this cross product. If you have the coordinates, a cross product is just multiply and subtract in the usual way. And what you find, kind of oddly, is that each one of the coordinates then of the cross product is a Jacobian determinant, which is weird because I thought the stretching factor was the magnitude of capital N. How come the coordinates of capital N seem to also individually be kind of little stretching factors? And further weird, I'm not looking at y and z as functions of s and t alone. It's x and y and z that are functions of t. So what is going on? Why do we have this? Why is this exactly a Jacobian determinant as are the next ones and the next one? So that's just an observation. It is going to come up later. And what's really going on underneath that and why that should happen is something I'm afraid we're not going to have time to talk about in this course. There's just not enough there's not enough minutes in the semester to get that done. But if you're curious, come talk to me in my office hours. I'll be very happy to show you. It's about a 10, 15-minute conversation, and I think it's very satisfying. And like I say, if you're curious, be happy to explain it. Okay. All right. Now there's a nice special case I want to show you. This is just a special case. We've got our general formula. But if you are using a graph parameterization, and remember, this is one of our major tools for parameterizing surfaces. So very often you will be using a graph parameterization, right? Well, the thing is, if it's a graph parameterization, then it immediately follows, this is what a graph parameterization is. Two of your coordinates are just going to be parameters. They are the parameters with respect to which you're taking the partials. That means you're going to get ones and zeros in these positions every time. Which means you're going to get a 1 in the cross product in this position every time. And furthermore, it means that these are going to be the partial derivatives of f. Well, negative, but still. Every time, and et cetera, et cetera. And you can further take the magnitude of this vector here, and you're going to get that expression every time. So this is a nice little shortcut. If you are using a graph parameterization of a function f, then here's your handy-dandy formula for your stretching factor. And feel free to just use that alone. It's fine. And then you don't have to repeat the process of taking the partials, taking the cross product, computing the magnitude. This formula has all that wrapped up in it. So very convenient. I like that a lot. I emphasize, though, this only works if you're using a graph parameterization. If you are not using a graph parameterization, this is garbage, doesn't make any sense at all, doesn't work at all. And sadly, very often, you won't be using a graph parameterization because your surface isn't a graph. And so that being the case, you can't use this at all. Pausing for questions. Does everybody see the limitations of this? All right. Okay, here's another neat observation about this. You just can't help but notice that is exactly the magnitude squared of the gradient. Weird. Just there it is, right? And then, hey, magnitude of the gradient. Magnitude of the gradient tells you how steep your graph is. Flashbacks to chapter 2. So another way to say this then is that if you're using a graph parameterization, then your stretching factor only depends on how steep is the graph. How about that? That's kind of neat. And let me show you an example where that's particularly useful. This is a very real-world thing. This is something that you might make use of in your future life if you're ever a homeowner and dealing with those trials and tribulations, which is a lot to keep track of. And someday you might have to put a roof on your house. And it is expensive. And you want to make sure that you're getting treated fairly by whoever it is that is going to put the roof on your house. And if they were to, perhaps overestimate the area of your roof by 30%, right? Then, they would overcharge you by 30%. And that would make it cost thousands of dollars more than it should. So we don't want that to happen. So how are you going to check them on that? Roofs are mostly graph parameterizations, right? I should say they're graphs. There's usually no roof underneath other roof. Maybe just a couple inches of overhang here or there, something like that. But mostly it's a graph. And so the stretching factor is just a function of the steepness. And here's another neat factor, another neat fact about roofs. Now, all exceptions granted. There's a lot of creative architecture out there, but many houses, I don't know if I'm quite comfortable saying most houses, but I wouldn't be surprised if it was most houses. The steepness, how steep is the roof, is approximately constant over the entire roof. In fact, they very often aim to have it's constant to the ability of the carpenter to cut it that accurately, right? And so what that means then is if you want to compute the surface area of the roof, and given that our stretching factor is just this function of the steepness, and given that the steepness is approximately constant, that means that this whole stretching factor is a constant, and it'll factor right outside of the integral. And lo and behold, as it turns out then, if you want to compute that surface area, you just need to know how steep is the roof, and then you just multiply then by the footprint area of the house. So that's much easier to measure. You don't have to climb up there and risk falling. Just do it with a tape measure, and you can make a simple little, rectangular polygon, and very, very simple geometry, and compute that area. And then again, multiply by this factor, and boom, you know the area of your roof. I think that's kind of a neat observation. The alternative, if you weren't aware of this trick, the direct way of computing the area would be you'd have to get up on your roof for one thing. It's already scary. And you're going to have to compute that, or measure that length right there. And you'd have to measure this length. And now you've got a geometry problem to figure out what the area of that triangle is. It's not a right triangle. So, you'd have to deal with that. And then you'd have to do likewise for each of the many little faces that you have on the roof of your house. And, again, keep in mind, now this is a very simple example of, kind of how they do roofs. And, they have these triangular things that kind of meet at vertices in the top. You could have far more than the 6 I have pictured here. You might have 20 such faces, depending on the gables and odd footprint that your house has, whatever. So computing a hard geometry problem on 20 triangles and parallelograms could be really a lot of work. This is much easier and much less risk of falling. Okay, what do you think? Questions? Everybody happy? By the way, this is a new addition to the lecture notes, and you may have noticed. I just put that in there. This afternoon. No, I guess it was this afternoon, early this afternoon. So I will update the notes on Sakai so you'll have a copy of this sometime soon. Okay. All right, moving along. That does section 7.1. So moving on now to surface integrals. This is what we've been kind of building up to. We kind of already have most of the work done on this. We just have to recognize that, in fact, we are already sort of mostly done with this. First, I make the innocent observation that if you have a surface in space, right, a surface in three-dimensional space, then just like if you had an area in the plane, or a solid in space, or a curve in the plane, or a curve in space, what have you, very often you're going to want to take that and chop it up into little pieces, and then add up on the little pieces. The chop it up, add it up strategy is extremely useful in just loads of situations. Here's an easy one. Let's suppose that there's a hill, or let's say a mountain, make it a little bit more dramatic. Anyway, on the side of this mountain, there is a certain flower that grows. But the flower is altitude sensitive. And so the amount, the density, the number of flowers per square foot is less at higher altitudes and greater at lower altitudes. Right? So depending then on the shape of the mountain, and how much area is there at those high altitudes? How much area is there at the lower altitudes where there's more flowers per unit area? How would you compute the total number of flowers on that mountain? And you can't just multiply density times area because the density varies, but you can chop it up into little pieces, and you can talk about on each little piece of area. You can just say, well, look, the number of flowers in that one little piece is going to be quantity per unit area times area. Right? And so whatever the area is of that little piece, multiplied by what the known concentration of flowers is for that altitude, and boom, there you go. And then you add up, of course, as usual, you add up over the entire surface. Does that look familiar? Same kind of thing we've done for several other contexts. We did that for two-dimensional regions in the plane. We've done something equivalent for three-dimensional regions in space, triple integrals. We've done something similar for line integrals. Curves in the plane, curves in space. This is just kind of the same idea. Okay. Is everybody comfortable with that? Okay. All right. Okay, so as usual, notation. I think that notation's pretty plausible, pretty familiar. We use two integral symbols because this is a two-index summation, because the surface over which we're adding is two-dimensional, right? And so here you go. There's a surface integral. And I'm going to give it a slightly different name. I'm going to call this a scalar surface integral. Two reasons. First of all, there's going to be a different kind of surface integral that we're going to see in a few minutes. I don't know, 5-10 minutes, something like that, real soon. And so we need to have names to distinguish the two different kinds of surface integrals from each other. You may recall we already did this with line integrals. Right? We had scalar line integrals, where your integrand was a scalar. And we had vector line integrals, where your integrand was a vector. Like if you're computing work, right, your integrand is force. That's a vector. Anyway, two different kinds of line integrals. We're going to find ourselves with two different kinds of surface integrals. And we use the term scalar because our integrand here is a scalar. Right? This is a scalar quantity, stuff per unit size. It's a scalar thing. And then furthermore, my differential here, also a scalar. That's not a vector differential. It's just area. Surface area of whatever you're looking at. Okay, so it's scalar surface integral. And believe it or not, we already know how to compute them. We just have to kind of put the pieces together. If you want to compute an integral over a surface that you have parametrized, keep in mind once you've got a parametrized surface, you can compute the partials. That means you can compute capital N. That means you can take the magnitude and get that stretching factor. That means that you know how output area relates to input area. Right? And now we just have to plug that in. So if I want to compute this integral right here, well, ds is magnitude of capital N times ds dt, as we saw in the last section. And magnitude of capital N is something that you can compute, this stretching factor. You can compute by looking at the parameterization and following the usual rules. And there you go, boom. And now we have this integral over here, this integral here. Everything there is all in terms of s's and t's. That's an integral in the st plane. It's just a plain old, regular old garden variety double integral at this point, and we know how to compute those. Everybody happy? Let's see an example. See this in action. So we're going to look back at the sphere. Suppose I'm looking at the unit sphere, but in fact, wait a second, just the upper half, right? So cut the sphere on the equator, let the bottom drop off. We're looking just at the kind of the dome part, the upper part of that unit sphere. And mass is distributed with density equal to z, so there's less density at the bottom, more density at the top for whatever weird reason. And how would I compute the mass? And then I'm going to, in parallel, since it's going to be very similar, I'm simultaneously going to compute the center of mass. And I'm simultaneously going to compute the moment of inertia around the z-axis. So, okay, the reason I'm going to do these all at once, just like we did with line integrals, they're going to be very, very similar calculations. All of these calculations are on the same sphere that we're going to parameterize with the same parameterization that has, therefore, the same stretching factor. And that's a very large part of the effort, just figuring out that stretching factor. So we might as well use that to compute all these things at the same time. Okay, now again, notice, big gap here. Yada, yada, yada. Got left out in here. So make sure you can fill in these gaps. This is the same exact calculation from a couple pages back where I outlined kind of the checkpoints of the partial derivatives and the cross product, etc. This is no checkpoints here. I think it'd be a good exercise to see if you can do the whole thing start to finish without looking at the checkpoints. But of course, they're there in the notes if you need them. But do make sure that you can do this calculation comfortably. Okay. All right. And with the stretching factor done, it's a matter of plugging in then to this formula, where that's where the stretching factor goes. We just have to plug in and off you go. So here it is. Mass accumulates. Mass is a sum of little pieces of mass. Here's the formula for the x-coordinate of the centroid. Likewise, we have, let's say, here's the z-coordinate of the centroid. There'd also be a calculation for the y-coordinate. But anyway, this is enough. And then don't forget moment of inertia. We have a standard formula for a moment of inertia, integral r squared dm. Okay. And dm, delta ds, that's the same in all these calculations. So that part of these calculations is the same. Let's see here. ds is stretching factor times d phi d theta in all of these calculations. That part's the same. Whoops, missed. There we go. Let's see here. Oh, what that stretching factor is, we already computed. It's sine phi. That's the same in all these calculations. Right? Everybody good so far? So I'm turning, Riemann sum scalar surface integrals into, you can see as we develop for each one of these, we're developing them down to just plain old double integrals. Oh, yeah, what are these, what are like x, y, and z? What's the deal with this x right here? What do I do with that x? Well, don't forget, x is given by the parameterization. It's the first coordinate of the parameterization. So x is sine phi cosine theta. Right? So everything that you need to simplify these scalar surface integrals that we write down in the abstract, it all comes from the parameterization and the stretching factor. Plug in, and you get double integrals that I'm going to leave, again, as exercises for y'all to compute. I know that y'all are good at double integrals, so you just crank those out. Everybody happy? Questions? Feel free. Let's hear some questions if you got them. Yeah, please.
What's the difference between the scalar surface integral and the double integral we met before?
Yeah, so that's a great question. So double integrals, as we saw back in early chapter 5, double integrals are integrals on two-dimensional regions that live inside of a two-dimensional space. Right? So if you have a two-dimensional region in the xy plane, specifically, so it's a two-dimensional thing, but it also lives in a two-dimensional world. Right? And that's the critical difference. That's what we don't have here. If I'm doing an integral that takes place on the side of a mountain, right? Well, that's a two-dimensional surface, but it's very importantly, it's got a shape to it. The side of the mountain is curved, and it's got up, and it's got left, right, and it's got north, south, right? I mean, it's got sort of it lives in a three-dimensional world, even though it itself is only two-dimensional.
Oh,
Yeah, that's the big distinction. I mean, you're right that they do have a lot in common in the sense that with both surface integrals and double integrals, you're multiplying quantity per unit area times area. That's the case in both, right? But the domains are fundamentally different. And scalar surface integrals present this problem of, I mean, how would I do this? I mean, surely it's not just dx dy because z matters, right? And it can't be dx dy dz because that would make it a triple. That would make it in volumes, and that doesn't make any sense. So from a iterated integral standpoint, it's just harder to deal with. And that's why we have to do this move here where we view it as an image and pull back, and then the point is we have an integral over here that is literally inside of two-dimensional space. And here we can do regular double integrals. Yeah, sure. Okay, great question. All right. Okay, moving along. So here is another kind of problem that we can address. I'm going to take us back to chapter 3 here real quick and talk about flux again. So you all remember flux, and the idea is that we asked the question. Suppose I have a vector field that represents velocity. I've got a fluid flowing around, and the vector field's telling me what the velocity of that fluid is, wherever I might happen to be looking. Then how would I compute the volume per unit time that's flowing through a given flat piece of surface? And the answer was this expression, right? That we then gave a name and a notation, and we call it flux. And then I asked a different question, and I said, okay, well, yeah, but what would happen if you multiplied density times volume? And the conclusion was that you get dm dt is computed by, well, this same formula, right? So let me say that all differently now. Chapter 3 told us that this formula, this thing called flux, is interesting in a couple of different scenarios. Depending on whether your vector field represents velocity or density times velocity, this thing called flux computes naturally interesting quantities. In some sense, how much fluid, be that by volume or by mass, whatever your context is, but how much fluid is flowing through your surface. And that's a naturally fundamentally interesting thing in that kind of a situation. Okay, so I hope everybody remembers all of that. This would be a good time, by the way, if it's been a while and maybe you kind of forgot where this formula came from. This is the picture that we were looking at, and you can of course rewind back to look at the chapter 3 notes or rewatch that lecture video or whatever works best for you, and remind yourself where that came from. Okay, so here's the thing. So this formula has some restrictions. It requires that the vector field be constant. So it's got to be the same vector field everywhere. It can't vary over the surface. If it varies, this whole thing crashes and burns. I mean, the fact that we could measure the quantity of fluid by claiming that it's a parallelepiped, it only becomes a parallelepiped if we assume that all these arrows representing fluid going through it are all the same. Right? Otherwise, we wouldn't get a parallelepiped. And furthermore, we also have to assume that the surface is flat. If that surface is anything other than flat, doesn't work. Right? Again, that's what gives us a parallelepiped that we can work with. So our formula here is very restricted, and we're going to entertain now the question of what if your vector field is not constant? Your vector field varies, right? Well, you can't use this formula anymore. That only works for constant vector fields. And furthermore, what if your surface is curved, aka not flat? Well, that's yet another reason we cannot use that formula to compute flux. I mean, I still might want to know how much fluid's flowing through my non-flat surface where the fluid is the non-constant velocity, right? It's still a natural question. But this formula fails. All right. Okay, I'm going to rewind back to chapter 6, just for comparison purposes. Y'all may recall this moment in chapter 6. And we had a similar situation. I mean, different, structurally similar, where, hey, here's a nice convenient little formula that allows us to compute work, but it has certain assumptions. It requires that the vector field be constant, and it requires that the displacement be on a straight path, aka flat. And we had to figure out, well, what are we going to do? How are we going to compute work? I mean, I'm still interested in work. Work is still a natural quantity of interest. How am I going to do that if the vector field's not constant, if the path is not straight? Can't use that formula anymore. What do? We chop it up into little pieces, etc. So I'm just pointing out that this is a familiar scenario. It's just flux instead of work and surface instead of curve. Anyway, it remains that we are again going to chop it up into little pieces, and the idea is that if you have your surface here that's curved, can't talk about flux yet through that curved surface. Yeah, but if I chop it up into a bunch of little itty bitty little pieces like this, on that little bitty piece, right, that's approximately flat. And the limit, as these pieces get smaller and smaller, you might believe that they approach flat. Right? And likewise, the vector field, now again, the vector field varies. Right? This field vector and that field vector are different, but those field vectors are evaluated at points that are pretty far from each other. Right? Those points are pretty far apart. These little pieces, all the points in them are pretty close together. And certainly, again, in the limit, as I chop finer and finer, they will necessarily always be even closer and closer together. And so you expect the vector field to not vary very much. Right? And so you expect the vector field on that little piece to be approximately constant. So this is our usual strategy. If you have bad news, bad things happening on a large scale, let's chop it up into a bunch of little pieces and deal with the pieces individually, and then add them up, as we do with all of our integrals that we've seen in this class. So strategically, does everybody see what I'm doing? Details to follow, of course. Everybody's happy? Okay. Excuse me. So, there was another issue when we were looking at work. I made the relatable, I hope, observation that if you're going up the hill, that is a different experience, right? Come from the alternative of going down the hill. Going up the hill takes positive amount of work. Going down the hill, easier. In fact, it takes technically a negative amount of work, right? And we talked about the idea of negative work. So how do you tell? I mean, if the question is, hey, I'd like to compute the work, just to ask the question, I need to know, well, which way are you going along the curve? And this is what an orientation is, right? We define an oriented curve to be not just a curve, but a curve with an indication of which direction is the direction that you're moving. And so we represented that with a unit tangent vector. We called this capital T. Right, capital T was an indication of what we're saying is the direction that we're actually going on that curve. And of course, there's two possible orientations on a curve. You can be going the one way on the curve or the other way. Right? Okay, hope that familiar. Everybody remember this? And now, by analogy, we have a similar situation here. If we're going to talk about flux through a surface, we need to we need to know, well, which direction is the positive direction through the surface. So if I've got here, for example, look at my hand here, if I've got a surface and there's water flowing around here, well, the water could be going this direction through the surface. Is that the positive direction? Do I count that as positive flux? Or Or is this the positive direction, in which case going through this way would be negative flux? Well, which is it? Well, it's just a question of what you're interested in computing. Just like here, there are two perfectly reasonable orientations on a curve, and you might, I suppose, want to know how much work it takes to go up the hill. You might, on the other hand, want to know how much work it takes to go down the hill. It's not a right or a wrong. We just need to have a clear indication of which direction on this curve is the direction we're going, and which direction is going backwards. Right? So, same with the surface. We need to have an indication of which direction is what we're going to call the positive direction through the surface. So we're going to represent the orientation with unit normal vectors. Well, I'll say unit vectors, and they need to indicate a direction through the surface, so they need to be normal to the surface. And so we call these orientation unit normals because they define the orientation. Okay, what do you think of that? Seem analogous? Everybody see how that's kind of analogous to the role that the unit tangent vectors played there. These being unit normal vectors because they're distinguishing directions through the surface. Okay. All right. Okay, so again, I claim we actually already know how to compute these things. We just kind of need to write down what we already know that we know how to do. If I want to, let me go back up to this picture here again. If I want to know how much flux there is through the entire surface, right, then I will look at one little piece of surface area at a time and then add up over the entire surface. So here's that. We add up over the entire surface. And then on any little single piece, looking at any little single piece here, the vector field's constant, the surface is flat. So we can use this formula, our old formula for flux, F dot n times the area. Right, that's what we have here. We're looking at a little piece of surface of area ds. So F dot n times ds is our chapter 3 formula for how you compute flux on flat surfaces with constant vector fields, which this is, for all intents and purposes. And lo and behold, we have an integral that we can compute. This is a surface integral, and we know how to compute surface integrals at this point. What do you think? Everybody all right? Okay. All right. Now, there's one last little thing I want to say about this, and that is a notational point, arguably. But let me remind you, when we were doing line integrals, one formula that we had for a vector line integral was this. Right, integral f dot t ds. But the other formula that we had for it was integral f dot dx. And this dx vector was actually the first way we wrote it down in the first place. Dx represents actual displacement along the curve. In other words, it's our vector differential. We were here. Then we move to there, and the act of displacing from here to there, that's a vector displacement. It's not just a distance. It's a distance in a certain direction. Namely, it's a vector displacement. And dx tells you both what direction are you going, and then also how far, what's the magnitude, how big is the piece that's going in that direction. So orientation and size, both wrapped up in this one dx vector. And we can rewrite it, and this is one of our rewrites that we did back in the last, let's see, what was that? Chapter 6, I guess it was. You can explicitly write dx as orientation, name of the direction that it's going, name of the unit tangent vector, times size, namely the length of that little piece of curve, which we've called ds. So this rewriting dx as TDS is, so again, old news. We did that back in, in chapter 6. So what I want to point out is, now arguably we could say we're in sort of the opposite situation here, but look at what we've got here. We've got n times d capital S. What do those represent? Well, n is our orientation. It's telling you how that little piece of surface is oriented in space. And ds is telling us size. So again, we find ourselves looking at this in ds there, direction and size of a little piece of our domain. Just like we saw, when we were doing line integrals here, TDS, direction and size. Now the size over here was a length instead of an area. The orientation was a tangent vector instead of a normal vector, but still, orientation and size we combine into a single thing called dx. And so following the kind of the pattern, orientation and size together here, we're going to wrap up into a single thing called ds. So the ds vector, the way I like to think about it is, it tells you everything you want to know about this little piece of surface. It tells you how is it oriented and how big is it. In the same way that dx tells you everything you'd want to know about a little piece of curve. How is it oriented and how big is it? Right, same deal. So, very handy notation, but also a really natural notation. And that gives us this alternative notation for integrals. Here, you can write integrals like that, but I prefer to write them like that. It's just notation, but again, I think it's natural and hey, it's also slightly fewer pen strokes, right? It's a little bit more compact. It's a little time saver, very convenient. And that's a non-trivial selling point. All right. Okay, so there you go. And by the way, now we have our, this is our other kind of integral that I'd promised to show you. So we have here, this is what we call a vector surface integral. I guess I didn't write that down, did I? Vector surface integral. Surface integral because, of course, this is an integral happening on a surface. And we call it a vector surface integral because, check it out, the integrand is a vector. It's literally a vector field. Right? The differential, also a vector. Right? At least when we write it like this. So both the differential and the integrand are vectors, and thus the name vector surface integral. What do you think? Everybody on board? Okay, not to be confused then with scalar surface integral, which is what we were talking about before. If you're counting flowers on a mountainside, that's a scalar surface integral because all the objects in question are scalars. If you're computing flux, the integrand is fundamentally a direction, right? It's a vector field that has direction. And the orientation of the surface matters in some sense. That doesn't matter with flowers, right? Flowers don't really, I guess sunlight, okay, sure, right? Okay, but if you know, for whatever reason, that your flowers on the side of the mountain are, have a certain amount of quantity per unit area, only the area matters. And how that piece of mountain is oriented doesn't matter. Right? Okay. All right. And let's see here. We are a little short on time. Is this a, let's see here. Okay. All right. Well, we've made it to, let me make the really quick, this is super quick observation. Don't forget we've already talked about parametrizing surfaces. And we already have formulas. We've already set up, we already know the stretching factor, and we know how to compute capital N. That's all done already. So I'm just going to make the innocent observation that having developed these formulas for how we compute flux, having computed these formulas for vector surface integrals, all I really have to do to turn this into something I can compute with is recall that ds is magnitude of capital N times dSdt. Right? That's just plugging in an old formula. And then seemingly innocently, I notice that here I have the unit normal vector times the magnitude of a normal vector. If you think about it, this product is the direction and the magnitude of capital N, so I'm just going to rewrite this as capital N, right? This little n is perpendicular to the surface, capital N is perpendicular to the surface. This product here has total magnitude capital N, magnitude of capital N. So does this. These vectors point in the same direction and have the same magnitude. They're the same vector, or so it would seem. And here is where I do want to confess I have committed a little math crime here, and I kind of want it to be obscured what the math crime is for the moment. You can read ahead if you'd like, but I think it'd also be a healthy exercise to chew on it. Try to see if you can identify for yourself what is wrong with the formula that I just wrote down here. And that'll be revealed on Wednesday, or again, if you read ahead a couple pages in the lecture notes. And we'll talk about that then. All right, y'all have a good day. See you later. And draw on the line right there.